Hello guys, in this video I'm gonna continue the Bode Plots, and this time I'm gonna check another standard form, which is a second order form. Second order means there is like omega square somewhere in each of omega, okay? And that basically will change a little bit the dynamics of the Bode Plots, although to be simple at the end, with like a little tip, that you might do or might not do based on your preference. So let's see. So in past lectures, we see like many standard forms like constant, zero origin, ball origin, simple zero, and simple pole. Okay. We didn't touch the quadratic zero or quadratic ball, which is basically the second order. Okay. If we look here, there is omega square. Look, guys, square. J omega over omega c squared. So there is a square. Okay, that what makes it second order. So if we form the h of omega in that form here or that form here, we're gonna get basically a high pass filter. Okay, either with positive or negative. Okay, transfer function. Because this is basically if omega is less than omega c, as you see here in this plot, the output will be zero. If omega again here is omega, if omega again is less than omega c, the output will be zero. Then the output will be positive and passes, or will be negative and but also will pass, but will pass inverted. So if there is 5 input, it will be 5 multiplied by minus something in the output. So it will pass. Okay. So that's the standard form. Let's understand it. So that lecture here is for just introduction. The next lecture, we're going to have 2 examples on that second order to see how to become more convenient in drawing such standard forms. Okay. So the standard form of second order h of omega is 1 plus j 2 zeta, very weird symbol zeta, which we do it like that, like 3, but we put like a notch in the top, a notch at the bottom. Okay, then omega over omega c plus j omega over omega c whole square. By the way, this is real. This is not imaginary, because if you square it, it will be minus omega square over omega c square, because j square is minus 1. Okay, but we like to write it in that way. Once you write again, in a question or a problem, it will be not like that. It will be much more complicated, or not complicated, sophisticated. I don't know. It will not be directly like that. So you have to make some simplification, take common factors until you reach that form. Okay, to be able to draw it or make the Bode plot for it. Okay, good. So let's see how to draw it. Okay. So again, when we draw 20 log h of omega. It's the magnitude of h of omega, of course. So 20 log magnitude of h of omega, which is 20 log all that stuff, the magnitude of all that stuff. 1 plus j omega over omega c square. I'm gonna switch the position, plus j 2 zeta omega over omega c. Okay, I'm gonna explain to you how these 2 drawings came from. Okay, of course, that case here is basically that case, which is the h of omega is positive at the high frequency, zero at the low frequency. So how it comes? Basically, if omega over omega c tend to be 0, like omega less than omega c is very small. Okay, so we can take the limit to that magnitude here. Okay, and in that case, 1 will be much bigger than j omega over omega c, with the magnitude of that, of course. And 1 also will be much bigger than the magnitude of j 2 zeta omega over omega c. So in that case, 20, in that case here, 20 log the magnitude of h of omega will be basically 20 log the magnitude of 1, which is 1. And the log 1 is basically 0. So that's why when we have low frequency, omega less than omega c, we have 20 log h of omega is 0. That's the first case. So the second case, omega over omega c tend to be infinity. Okay. In that case here, we're gonna neglect two terms. We're gonna neglect the one, and we're gonna neglect also that term here. Basically, you can write it in that way because the magnitude of all that equation here, or all that term here, is basically the square root of the real square, 1 plus j omega over omega c square whole is square, okay, plus j, I'm sorry, without j, has to be without j, 2 zeta omega over omega c square, okay. So when omega over omega c tend to be infinity, look, that term here is omega to the power of 4, or omega over omega c to the power of 4. And that term here will give you omega over omega c to the power of 2. So when omega over omega c is much, tend to be infinity, of course, omega to the power divided by omega c will be much, much higher than omega over omega c to the power of 2. So that guy is going to be neglected, okay, or tended to be 0. So that will end up like that. 1 plus j omega over omega c square, and all of that is square. Okay? And again, of omega over omega c tended to be infinity, so 1 is much lower than omega over omega c. So that by term will end up like that, square root of j omega over omega c square, and here we have another square, and that will be omega over omega c square. Okay, so that will, so at the end of the day, 20 log the magnitude of h of omega when omega over omega c tends to be infinity, that will be 20 log omega over omega c square, which is 40 log omega over omega c. Okay, let's now draw that. Okay, so we're gonna have like a linear y-axis and the logarithmic x-axis. The x-axis is omega, and we're gonna make like the text of the x-axis in terms of omega. Like here, for example, 0.1 omega c, then here 1 omega c, 10 omega c, 10 to the power of 2, 100 omega c, 1000 omega c, 10,000 omega c, and so on. Okay. The y-axis, let's make it in 20s. So 20 decibels, 40 decibels, 60 decibels, 80 decibels, 100 decibels. And same here, minus 20, minus 40, minus 80. And let's take some examples. First here, when omega equal to omega c, that will be log 1. Log 1 is 0, so that will be 0. When omega equal to 10 omega c, that will be 40 log 10. Log 10 is 1, so that will be plus 40. Omega equal to 100 omega c, that will be log 100, and log 100 is 2. 2 multiplied by 4 is 80. Can continue 1000 omega c, that will be 120, and so on. So here we increase by 40, like the other ones was the increase usually is by 20. Okay, let's draw that. So first of all, For number one, when omega less than omega c, that's 0. Then at omega c, h of omega is still 0. At omega c, it's 40. At 100 omega c, it's 80. 1000 omega c, it's 120. So here is 100, this is 120. Okay. That's high pass filter. Okay. But the rate here, the rate or the slope is 40 decibels per decade. We learn what is decade means. The decade is the distance between two successive points on the w-axis or omega, sorry, omega axis, the frequency axis, the x-axis. That's a decade. So when we move from a decade to another decade, we have an increase of 40 decibels in our h of omega. Okay, if we look here, let's compare the symbol 0 or zero origin by symbol 0 and the quadratic 0. Here the slope is 20n because the n here, when n is 1, it's 20. When the symbol 0 again 20n and again take n equal to 1, that's a 20. For the quadratic 0, it's a 40n. So it's a double. It's more steep. It's more steep. Okay, so the rise is more steep. Let's see the rise if the rise was 20. If the rise was 20, that's not like our question, but if the rise is 20, it will be here, here, and here. That will be the rise if it's a 20 decibel per decade. So which is more steep or which is steeper, the 40 or the 20? Of course, as you see here, the 40. Okay, you have more slope here. Okay, that's basically why we use this quadratic, or why this quadratic, or basically second order h of omega is important. Because if you want to play with the rate of increase or the rate of decrease, you have to adopt this one because it increases, your rate. Okay, guys, that's basically, the second order in its simplest form. Now let's talk about the new term here, zeta. Okay, so that's not the end of the game. We have to adopt something related to zeta. So zeta will change something. So let's go back to our question and see what zeta will change. Okay, it's easy. So zeta will change a little bit that form. Okay, so the question is the condition is as follows. Zeta has two conditions. It's either less than 1 over square root of 2. Okay. The second condition is that zeta higher than 1 over the square root of 2. Okay. So I'm going to do this with two colors. Let's first take the first condition. Zeta is less than 1 over the square root. If you calculate zeta and you find it less than 1 over the square root of 2, then there is what's called some resonance. Okay. And some peak, we call it resonant peak. Okay. So the slope will not be, or the shape, the final shape, when you draw it correctly or accurately on MATLAB, for example, it will not be like that. It will have some curvature with a peak. We call it resonant peak. Okay. So in that case here, it will be something like that. Look, guys, approximately 1 decade before omega c, we get down. At omega c, we make a peak. This called is resonant or resonance peak. Then we rise again, and approximately 1 decade after omega c, we meet up with the curve again. Okay. if if zeta is less than 1 over the square root of square root of 2. So how much we go down here? How much is this peak? This peak is 20 log 1 over 2 zeta square root of 1 minus zeta square. Okay. So if, for example, this end to be, for example, minus 20, that's why we end up to minus 20, for example. Okay. It might be less than that or higher than that, whatever. Okay. What happens now if zeta is higher than the square root of 2? So let's have another color. Like this color, for example. If in that case, it will be like a smooth one. So again, one decade before omega c, we rise, we make a small curvature, and then we meet up again with the curve, the red curve, and one decade after the omega c, and we continue movement linearly. Okay. So the change only in the area one decade after, one decade, I'm sorry, one decade before, one decade after omega c. It's either you go down like that and go up again, or you just make it smooth, you know, around omega c. Okay, guys, that's basically, you know, how zeta interact with our like curve. Does we do we like care about that in our course? In our course, no. But so if you are belonging to our course, circuit, you know, AC circuits course, you don't have to do that. So the red curve that we draw before, it's okay. You don't have to do even that or that. It's okay. Okay. You don't have to do the smoothing or the red or the, I'm sorry, the green or this like sky blue like curvature. Okay, the red is enough. But if you like, you know, from one someone that doesn't belong to our course, this is basically how to do it. Okay, you have to consider zeta. Okay, and if zeta is less than 1 over the square root of 2, you do this peak resonance. If this zeta is higher than square root of 1 over the square root of 2, it will be like smoothing one decade before to one decade. Okay, guys, that's basically introduction about, you know, second order Bode plots. In the next lecture, we're gonna see 2 examples on that. Thank you very much for watching, and see you in the next video. Bye.